We work with class node as in the previous video. We develop a method that can serve as a model for recursive methods that look for a node with a certain property. That property will be the value of the node, but there are other possibilities. We could search for any leaf, a leaf with a certain value, or the parent of a node with a certain value. To the right, we show a tree with 3 children, numbered 1, 2, 3. There could be fewer children or more. We write the method body based on the method specification and header. Since t may be null, representing an empty tree, we take care of that case first. If t is null, return null. The second case is to determine whether root t is the desired node. If t.val equals v, return t. The third step is to check each child of t in turn to see whether the subtree with that child as root contains a node with value v. If so, return it. This requires a for each loop that, at each iteration, processes a child, which we name ch. How is subtree ch to be processed? The function specification says that if the function is called with ch as the first parameter, it will return the node within the subtree ch that has the value v, or null, if such a node doesn't exist. Therefore, the body of the loop is, if getNode chv is not null, return getNode chv. But look, there are 2 calls of getNode with the same arguments. In the worst case, all parts of the tree will be traversed twice, and for a large tree, that can be very expensive. When writing methods that may traverse large data structures, avoid duplicate work whenever possible. So we introduce a local variable and rewrite the loop body. First, assign getNode chv to a new local variable n. Then, if n is not null, return n. Finally, if no child contains a node with value v, the loop terminates normally. Therefore, after the loop, null must be returned. Use this method as a model for any function that looks for a node with a certain property. It is a design pattern consisting of 4 steps. 1. Base case. Process an empty tree. 2. Base case. Check the root. 3. Recursive case. Check each child in turn, returning a suitable node if the property is found. And 4. Take care of the case that no node has the property. There will be differences, of course. For example, a precondition might be that the parameter t is not null, and testing whether a node has a certain property may be more complicated. We make several points about the development and the resulting method. 1. Avoid extra unnecessary case analysis. Some people put this statement before the for each loop. If t.children is empty, return null. This statement is unnecessary and makes the method less efficient. The for each loop processes the case of 0 children appropriately. The loop terminates immediately, executing 0 iterations, and after that, the statement return null is executed. 2. Avoid the use of a break statement to terminate the loop. If a break statement is used in the case that a child subtree contains the desired property, the code after the loop becomes more complicated. 3. Don't traverse the tree unnecessarily. A function contains tv is likely to be available, and the tendency is to insert a statement that tests whether t contains v and to return null if it doesn't. The extra traversal of the tree is unnecessary. 4. Avoid unnecessary structure. We did not write the method body to test whether t is not null, processing the non-empty tree in the then part. This introduces more complexity, an extra unnecessary level of nesting. Further, if the code to process a non-empty tree is long, it will become difficult to remember why the final statement returns null. Handle the cases as we did, one at a time, with each case doing what is necessary.